Welcome back. We have been studying about shunt compensation till now. Let's move on to series compensation. So the fundamental difference between shunt compensation as well as series compensation is that in shunt compensation we are actually adding the element in a shunt mode, or we are adding the element at intermittent intervals in the transmission system. At that system, the compensator is added in shunt mode, whereas in series compensator what we are actually doing is we are actually inserting one compensating component, that is the reactive power compensating component, in series with the transmission line. So basically if you want to reduce the reactive power consumption in the transmission system, so we will simply do what we can simply do is we can compensate for whatever inductive reactance there is in the transmission system with some capacitive reactance. So that could be a fundamental idea, or that's readily what might come to our mind. So by considering this kind of compensation system, where this figure A is showing, it's a single line diagram, or you can say a circuit representation of a transmission line, where X represents the transmission reactance and Xc is our compensating capacitor, which compensates the effects of X, and the value of Xc is variable such that the extent of the compensation can be controlled. That is, if we want to compensate X completely, or if we want to compensate X in a partial manner, that is whether in case of low loading conditions the overcompensation might lead to have high voltages on the receiving side. So basically what we are actually trying to do is make this particular arrangement, or our compensation device, be applicable in all the situations or all the operational scenarios that a power system or a power transmission system might encounter. So the fundamental difference that we have discussed between shunt and series compensation was one was regarding how they are getting connected in the transmission system. Another one is based on the effect in which they are compensating. That is, when you are adding a shunt compensation device, you are actually connecting that particular device in a shunt manner, which means that it's actually acting as a current source which injects a controlled current that would compensate, a controlled reactive current that would compensate, or that would provide whatever is the reactive power that is required by the system so as to improve its performance. Whereas when you are adding a series component like what we have here, we are actually adding is a controlled voltage source, which is added in series between the source, or between the actual generator and also the load. So this particular reactive voltage source, which when or it's basically a voltage source which would control what is the power flow between the 2 points. So we know that Vs is equal to this V, whatever the voltage is across the capacitor, the voltage across the inductor, plus the voltage across the load, or we can say that the sending end and receiving end. So that's why Vs and Vr. So if we can consider this transmission line as a whole thing, then the voltage across the line, that let's call it V, then Vs is equal to Vl plus Vr, and by varying the voltage across this particular capacitor, we can control what is the voltage, that is voltage loss on the transmission line, or the voltage drop on the transmission line. Thus we can control what is the receiving end voltage, and also what is the voltage drop, or what is the power loss that's taking place in the transmission line. Thus, but how do we control what are the other aspects of the transmission system? Let's look at that particular idea. Okay, see here, we have a two-bus system where one area which connects, or a two-bus system, that is one transmission line, two buses, and the buses belong to different areas in a transmission power system. So the power, or the active power that's flowing from one particular area to another, that can be calculated by using this particular formula. This formula that's colored in the green color, that is the product of magnitudes of the sending end voltage and the receiving end voltage, that is V1 into V2, divided by what is the separating impedance in between the two buses, X, multiplied by sine of the angle difference between the sending end and receiving end. If it's the other way around, it would be theta 2 minus theta 1. So we can see that this P from 1 to 2 would be equal to P of 2 to 1. So basically that should mean the same thing. So Here we can see that if we keep the voltage magnitudes constant and the sign of the values, let's consider v1 v2 sine of theta 1 minus theta 2 to be more or less a constant at this point of time, and then in that particular perspective we can say that the active power that's being transferred from point 1 to point 2 is actually inversely proportional to what is the reactance that's separating the 2 points. So if we can control, that is, if we are adding a series compensator, what we are actually doing is we are compensating for the transmission line reactance, which is actually separating the buses 1 and 2. So what we are actually doing is, what we are actually having is the scope to control even the active power flow between the points 1 and 2. So at the same voltage and at the same angle difference, that is at the same voltage magnitudes and at the same angle difference, we can transmit more power if we can control, or if we can reduce the value of x here. So by reducing the value of x, we can transmit more amount of active power at the same initial conditions as in the case when there was no compensating device. Also, we can see that v1 v2 by x, which is the peak when we plot p versus theta 1 minus theta 2, a sinusoid curve, the peak value is going to be v1 into v2 divided by x, which is nothing but the maximum power transfer capability from the points 1 to 2. So this maximum value will also get improved if we can reduce the value of x. This is also coming as a advantage, or is coming as another control aspect when we are employing series series compensators. So to exploit this possibility, what does this mean? That is, we can have more power being transferred from the sending end to the receiving end at the same value of theta, that is at the same previous value of theta when there was no compensator, at the same previous value of magnitudes when there was no series compensator. So basically we can support a larger load under the same conditions. That means an improvement in voltage stability, that means an improvement in transient stability or the angle stability. So series compensation brings about so much of control into the system when compared to shunt compensation, as according to me. But the risk is we are actually adding a series component in the transmission line, and that component, if it fails, the entire system is going to fail. So there are pros, there are cons. Let's see what is the basic principle of compensation while using a series compensator, and then we can see what are the different kinds of series compensators and learn what are the pros and cons of each of them one by one. As we have been discussing, when we are adding a capacitive compensation with the series transmission line, that is, X is the transmission line reactance and Xc is the reactance of the compensating series compensator. So the effective reactance of the transmission line is going to be X minus Xc, which also gives us a possibility of expressing our reactance, that is our Xc, as a function of X, that is what is the amount of inductive reactance that is being compensated. That particular, physically, that would mean what is known as the degree of series compensation, that is to what extent does our compensator compensate the effect of the transmission line. When we are having peak load periods, or when we are having heavy loads, we would need more of compensation because the current through the inductance is more and the voltage drop through the inductance is more, and that much of compensation is not needed when we are having a light load period. That would mean the current through the inductance is lower and maybe much lower, and in such a situation we do not need such a high level of compensation, as it might increase the end level voltage to a very high value. So in such situations, what we actually need is a variable or controllable compensation, and how much of the amount is supposed to be controlled, which can be determined by knowing what is the degree of series compensation. The curve figure B, it shows the PV curve of our generator of the system on the figure A, and in that you can see that the voltage for different values of Xc, you are having a different value of knee point, that is in this particular PV curve, what we call this particular P value, or the value at which the power transmitted is at maximum, we call that a knee point, where beyond that, that is the maximum point theoretically possible to be attained, and beyond that the system is going to collapse. And by increasing the value of Xc, we are attaining a higher, much higher value of the maximum power that can be transferred, and that too at the same value of voltage. If you can see, almost all this maximum point, they match at the same voltage level, more or less. So what we can see is the voltage drop, even under the same voltage drop, we could make our system, or we could subject, or we could transfer more amount of power from the sending end to the receiving end under these conditions. Also at one particular voltage, that is, if you can see, if you consider a point just below what is what we call as 1 per unit, maybe we can take it as 1.95 per unit. So if you consider a transmission line in this, or if you consider the power transfer at these particular points, or at that particular voltage, you can see that it's increasing. That is, it's increasing, and the increase is not just in a simple manner, it's actually per unit that we are giving here. So if it is 1 megawatt, increase in half per unit means it's increasing 0.5 megawatts. That's not a small amount of power. So by using series compensator, we are able to achieve such gigantic changes into the operation of our transmission line. So what this means is, for transferring the same amount of power, we only need to subject our system to a lower, or we only need to have a lower voltage drop across the transmission line, which means an improvement in the system voltage profile. That is, we are improving the voltage stability. Also, we are able to transfer a larger amount of power, a larger amount of active power under the same voltage levels. That is, we are improving the transient stability of our system, or the voltage angle, or the active power stability of the system. Also, along with that, we are physically, or like from the retrofitting, or from the infrastructure point of view, what we can say is that for the same transmission line, and under the same situation, with the same generator, the same transmission line, the same substation and all, what we are doing is, by adding a simple series compensator, not that simple, but compared to the other devices, a much less complex and much cheaper series compensation device, we are able to transfer a much larger amount of power under the same circumstances. So that is what the source of what is the extent of impact that these devices bring into this. Moving on to the different types of series compensators, we have variable impedance type series compensator, just as similar in the case of shunt compensation. That is, this is the idea that we have been familiarizing in the last few minutes. That is, we are actually compensating the impedance in the or the inductive reactance in the transmission line by adding a variable capacitive reactance into the system. So basically, we are varying what is the impedance in the entire transmission line. One of the most common example of the variable impedance type series compensator is the gate turn-off controlled series capacitor, in short GCSC. How is it different from the previous types of controllers that we have learned in the shunt compensation side? Is there we have been only using simple thyristors where turn off is not an option, but here we are using is a gate turn off thyristor, but not the other way around. The operation of a basic gate turn off thyristor is gate turn off the thyristor based series capacitor compensator is what is given here. So figure A shows the fundamental structure, that is, you have a bidirectional gate turn off thyristor which is in parallel with a series capacitor, and the capacitor is connected in series with is parallel with the series capacitor in the sense that it is connected in series with the transmission line. So evidently, when this particular switch and any of these switches are on, the voltage across the capacitor is 0, and when these switches are not conducting, they are switched on, there is a voltage across the capacitor. So by controlling the conduction period of these switches, we can control what is the voltage across the capacitor, and thus by controlling the voltage across the capacitor, we can control what is the current that is flowing through the transmission line. We'll study about this in the following lectures. Thank you.